Welcome back, everybody. Now we are going to hear about a new state of a new safe external debugger interface for CPython. Please give a warm welcome to Pablo Galindo Salgado and Ivona Stojanovic.
All right, thank you all for coming. So before I start, I have the pleasure. So I have the pleasure to give this talk with Ivona. So this is not only her first Python, but it's also her first talk ever. So I would like a big round of applause for her. All right. She speaks slower than I, so you will actually understand her parts. All right. So before I start, I would like you to imagine a technology so different and so profound that is able to basically reach into the hydrogen atoms in your body and basically align all the spins of those atoms and just wait for the whispers of those atoms just to reconstruct how your organs look like. This sounds like science fiction, but it's actually not. This is the MRI technology. This machine creates a magnetic field that is 60 times stronger than the magnetic field of the Earth. And this thing is basically used to analyze how all the organs that you have look like. This was used for the first time in 1977, and it basically revolutionized and changed the very foundation of medicine. So this is going to be our little metaphor for debugging. So does Python debugging look like an MRI machine? Well, Python debugging looks more like this. Here you can see two senior engineers and the manager, the live debugging Python application. You can know who is the manager because he has the book and looks like he's helping, but no. Sorry. All right. So this is interesting because the metaphor actually works. Because if you look at how all medicine look like, it looks crazy, right? Because all right, yeah. Sorry about this. We should have debugged this a bit early. All right. So the metaphor actually works very well because if you look at how old medicine used to look like, it was quite crazy. Some people would say it was bananas. Whoops. So it was so ridiculous. They were using leeches attached to you just because you have bad spirits attached to it. If you have a headache, they used to drill into your head just to relieve that. And if you have any kind of mental illness, they used to put you in cold water just to somehow reset your brain. Right? So I'm going to convince you that this is kind of how we debug programs today in Python. And what I'm going to present to you is Python's MRI moment, what I think is the first time the whole thing changes. So today, I think Python debugging is basically trapped in the pre-MRI era. We are basically practicing the software equivalent of drilling holes into skulls, and basically we are believing that it's helping. So for instance, imagine that you have a Python application and it's doing something weird, something unexpected. How would you debug this thing? So the only way to debug this in these days is that you kill the process, you just terminate the process, then you restart the process with your debugging tools attached, PDB or whatever it is, and then you hope that the problem happens again in exactly the same way. Right? So this is the software equivalent to say that this patient is sick. So let's just kill them, let's resurrect them in our laboratory, and just let's hope that they get sick in the same way so we can observe it. Kind of not great, right? So if doctors treat patients this way, they will lose their licenses, right? But somehow we are dealing with programs that are basically driving the whole world, and somehow this is considered standard practice. So there are some tools that do a bit further. They try to go a bit further. So for instance, imagine that you have two processes. What is the state of the art of debugging these days? Well, it's used native debugging. That's why I'm using this cog here and not a Python logo. So the way you will debug process using native debugging is that you use system calls like ptrace. And this is a system call the Linux kernel exposes that allows you to just reach to another process and attach to it. And then you can do a bunch of evil things. For example, you can wait until the process is asleep, so the system call has actually worked. And then you can start basically to inspect the state. So you can call ptrace get registers to get the register, so what the hell the process is doing right now. You can actually like pick up memory, so you can copy memory from the process. This actual call is very inefficient, but it will get you like what is going on. And you can actually even use this poke test to actually change the memory. So you can change the memory of the process. For instance, here I'm changing the instruction pointer just to force the process to execute some different code. You can use this, if you know what a function is, to change the instruction pointer and force the process to execute a different function. This will be useful, for instance, if you want to print a variable, a complicated one, right? Not just read memory, or to force the process to execute something else that will tell you what's going on. Imagine changing the debug level or something like that. So normally, if you do this in Python, you will do all these things. You will do your debugging. You will call ptraceCon to force the process to continue, and you know what will happen? The thing will explode. Why it will explode? Because happens that there are some system calls and some functions called in libc that have problems. The classic one is malloc. Why this is a problem? Well, the problem is that malloc has a lock. So if you just happen to attach while you are under malloc and you yourself call malloc again, you are deadlocking because you are trying to acquire the same lock. So this is the fundamental problem of this approach. The fundamental problem is that you don't know what's going on in the process when you attach. You're attaching at a random moment that the process is not ready to, and then you're trying to call functions. So you just cannot do this. There are some tools, like some debuggers that we maintain, that try to work around this by like putting breakpoint on all the evil functions and stop before entering the function and then calling the actual code that you want before entering the function that you want. But as you see, the moment you start seeing this list, you will be very nervous because you know that the consequences of missing one of these is actually not great. And just to give you a snippet of the kind of things that a debugger will do, once you hit one of these points, you may like just open an entire set object full of code, which is like very much not safe. So this is the problem. The problem is that this approach can basically make your process crash completely while you're attaching. And this is unacceptable, especially if you're trying to debug a production application. And restarting these applications is very heavy, so you don't want to do that. So basically the problem is that we cannot just have two processes talk to each other like this. Python likes to basically talk with bytecode, but we cannot say bytecode from one process to the other and tell the other Python process what to do. Like this is not possible, it won't work. So the only hope that you have, these days at least, is to use native debuggers like GDB, and which speak a different language, speak the language of C and symbols and ABIs and whatnot. But then all the Python code is lost. Now you are forced to speak the C language, and this is not what you want. You want to see your Python functions, you want to see your Python coroutines, your async your stuff. So basically the problem is that these two guys are speaking different languages. And what we want is that they speak the same language. So some tools actually do a similar thing. They are not debuggers, but they are program inspectors or profilers. There are some of them that we maintain, and there are some others that are very popular. So all of these programs are able to analyze what is happening in a different program. They are not able to change it. They are not able to like force calls and do complicated things. They are able to only observe. And to do that, they use this system called process VM readb. It's a way to just read memory. And then I was like remembering Inception, and they have this fantastic quote that if you can steal an idea from someone else, maybe you can also plan one instead. So I just discovered that obviously not only there is process being read B, but there's also process being write B. And this was the idea that sparked PEP 678, that is a PEP that I did with Ivona and Matt Wodniski. And we worked really, really, really hard, like the PEP is bananas, to give you a way to debug Python processes without crashing them. And Ivona is going to explain how this thing works.
Okay. So Pablo explained us how the traditional debuggers work and why they're unsafe, but let's see how we implement this in CPython. So here, let's start by looking how this mechanism works from a high-level perspective. On the left side, you have a debugger or any external tool that wants to attach to the running Python process. And on the right, you have a running Python process with a process ID 1234, and the interpreter that is managing the execution of that process. And let's say that our debugger wants to run some code inside our Python process. So what will the debugger do? You can look at the debugger as kind of like a manager. So the interpreter here will be like a hardworking employee who is in the middle of something. So the debugger doesn't want to interrupt the interpreter. He just wants to assign the task to the interpreter and just say, when you're ready, just execute this. You can look at this as a debugger, like sliding a sticky note to the interpreter. So what we did, we added a new function, remote exec, which uses a process ID and a path to the script. So that is like our sticky note to the interpreter. So what will the interpreter do? It will wait until it reaches a save point. By save point, it means that the interpreter is not doing any serious business. It's not like in the middle of the garbage collection or memory allocation or some like serious stuff. So when the interpreter hits a save point, it will execute the script.py that we wanted. So here we have a simple example. We're going to generate a script.py, and after that we're going to open the script and dump like a simple print statement. So after that we're going to call remote exec with the process ID and the path to the script. But you might be wondering, why are we using a file here and not like just a raw code? So for that you're going to wait a little bit longer. And another question that we can ask here is where this print will be printed. Like, will we see hello from remote in the debugger or at the Python process? As we want to execute the code in the remote process, so hello from remote will be printed in the remote process. So we mentioned that the interpreter waits to hit the save point in order to run the script. But when do save points occur? So for that, we rely on something that is called eval loop or evaluation loop. So eval loop is the part of the interpreter that runs, that executes the bytecode. So here we have a simple function foo that adds two numbers and multiplies the result and returns the results. And when we disassemble this code, we're gonna have something like this. So here is where it gets interesting. So when the interpreter loop is running, it's going to go and execute the bytecode instructions one by one. And at some point, what the interpreter will do, it will pause for a moment and it will ask, hey, is there something that needs to be done before I move on? And what the interpreter will do, it will check something that is called eval breaker. So you can look at the eval breaker as like a lightweight check, where the interpreter checks something like, for example, is there any signal that I need to handle, or like a thread switch? Or in our case, we use this place to check if somebody requested a remote debugging. So the interpreter here will check if there is a script to be run. So what we did so far, we call the remote exec, we pass the process ID and the script. But how does the debugger know where is how to notify the interpreter there is something to be run? So for that, we're gonna give a debugger a box. So both the debugger and the interpreter can access this box. So what the debugger will do, it will find the box, it will drop the script in the box, and it will raise like a small alarm, let's say, to notify the interpreter, hey, there is something that you can run. And what will the interpreter do? It will open up the box, and it will check if there is a script to be run. But there is a problem here. Like, how do we find this box? So for that, somehow we need to navigate our debugger like to find a box. So for that, we're going to give the debugger a map. And in order like, to find a map, we're using something like PyRuntime. So PyRuntime is internal CPython structure that holds the interpreter's global state. And it also holds like a lot of important internal data, such as interpreters lists or like thread states. So in order like to communicate with the process, debugger needs to locate PyRuntime. But the problem with that is the PyRuntime is changing, the memory of the address of PyRuntime is changing all the time. So it depends on how the binary was loaded. So for that, we have like the next task. So we need to figure out how to locate PyRuntime. So the first thing that we need to do, we need to locate PyRuntime inside the binary. So what we're going to do, we're going to use something that we added before, like a metadata that is going to show us where in the binary PyRuntime is. So if you use a tool such as readelf, you can inspect the binary and you can see the binary structure. So here we can see that we have PyRuntime, and this address is actually the offset where the PyRuntime is inside the binary. So once we have the offset, the offset is just like the relative position like to the start of the binary, right? So the offset is not enough. We need to figure out where the binary is loaded. So for that, the next thing that we need to do is to figure out where the binary was loaded. So in Linux, we're using something called procmaps. It's a file provided by kernel that gives you a memory mapping of the given process. So for that, we're going to look for the entries of Python executable or shared object, which show us where the binary is loaded. So here, when we open that file, we see Python, and this address is actually where our binary is loaded. So once we have this address, we need to do some serious math here. So we're just gonna add the offset, and voila, we have the address of PyRuntime. So once we found PyRuntime, Pablo mentioned process VM read wheel earlier. So that's a system call that allows us to read the memory of another Python process. So we're going to use that one, and we're going to read the memory, and we have our PyRuntime. But again, we have another problem because PyRuntime structure changes over the versions, or not even the version. It can be different like in the same version. So somehow we need to know which bytes are we reading. So for that, we're going to use something that is at the start of PyRuntime, which is called PyDebugOffsets. So you can look at PyDebugOffset like a way, like a schema to figure out like what bytes are you reading. For example, if you want to read like free-threaded bytes, you're going to go to this guy and you see there is like a free-threaded offset. So you're going to use that guy. So what we actually did to find our box is we extended PyDebugOffsets with a really simple structure called debugger support. This structure has 5 fields, but I'm not going to explain all 5. I'm just going to explain the 2 important ones, which is remote debugger pending call, which you remember like the alarm that we mentioned earlier that debugger indicates to interpreter there is something to be run, and debugger script path. This one is the offset in our box where we should drop, where debugger should drop the script. So let's go to the path how we actually find the box. So we started with a map, and we need a path to follow some path, right? And after that, we have a list of interpreters, so we need to choose the right one. So when we choose the right one, interpreter has a list of threads. So when we reach a particular thread, there's the place where our box is. So at the very end, we have the 2 fields that we mentioned earlier. So the bottom, like the purple box, is actually our box from the beginning. So what we did so far, we showed you how we made the debugger write to this box. But we need to figure out how the interpreter will read this box. So here we have a code that might look scary to you, but you don't need to understand everything here. So we're going to just go through some lines that are highlighted. As we mentioned before, the interpreter will only run this code when it's safe. So an interpreter will check the eval breaker, which is our save point, and if the eval breaker is set, it's going to check if somebody requested a remote debugging. And somebody did, it will open up the script and execute the script. And here, what we also are doing is calling PySysAudit just to notify some people that we are running some code. And also, I think this is a perfect part where we should answer the question that we mentioned before. Why are we using a file and not raw bytes? So just imagine that we have an attacker and that wants to execute some evil code. So it will run evil code in our box and it will execute it, right? But if we have a file, the attacker needs to have a permission to write to the operating system. So we have like additional layer of security here, right? And so far, what we did, we just added one function and we just wrote to the box, right? So you might think this is like pretty easy, but let me show you what is actually behind this error that's supposed to show you like, oh, we just wrote to the box. So this might look scary, right? So it's not like simple as we thought at the beginning. So I'll pass to Pablo so he can wrap this up.
All right. So after this journey, you may be saying, all right, Pablo, this is kind of very cool, and you can execute code in a different process. But as Mark Shannon will point out, this looks like remote execution as a service. So I don't trust you. You can trust me, I'm a respectable person. So apart from that, if you don't still trust me, don't worry, because I gave you a way to basically deactivate this behavior. So there is many ways depending on your level of paranoid. The easier one is an environment variable called Python disable remote debug. So if you set this to anything, even the empty string, then the process will refuse to execute anything. Right? So you can just put this environment variable, it will affect all Python processes. If you want to just affect one, you can use this -x like a command line argument to the Python interpreter that will just stop the remote debugging for that. If you happen to be working on some ridiculous place where like trusting Pablo is a crime or something like that, you can go the nuclear way and use basically this flag when you compile interpreter. So you will need to recompile interpreter yourself. But if you could pass this flag to the configure script, then the code that actually enables all of this will not be even compiled in Python. So there's no way, no one can use this machinery for anything. So just if it's the case. So obviously, I want you to think about this as a building block, right? We give you, or we are giving tool authors and debugger implementers the possibility of executing code in a remote process safely. So this is not for you to use directly if you're a user. This is for tool authors to leverage. But we wanted to give you some cool thing for Python 3.14 that you are excited. And I've been basically waiting forever to have this. This has been a dream of mine, just because every single time I thought, wouldn't this be cool? People told me it was impossible. And now I can smile to you and say, we did it. So in Python 3.14, you will have remote PDB. So you can have PDB, and you can pass this -p argument over there. You can pass IP ID, and you can attach to running process using PDB. This means that you can have some process over here in the right. So imagine that it's on the repo. And then on the left, you can basically imagine that you have some variable there. On the left, you basically can have another Python process. You call Python -n PDB, you give this PID, and then you have a PDB session that is inspecting the other one without stopping it, or restarting it, or killing it. And then when you finish to inspect whatever, you can call functions, you can print variables, you can do whatever you can do in PDB. And when you finish, you can press continue, it detaches, and the program continues. So apart from that, people can start building a lot of other tools, because this ability to like execute code in a different process can basically use to change the status of the process for debugging purposes. For example, imagine that you have a web server that is doing something weird. It's emitting a bunch of warnings, but it's not enough to know what it is. Well, you can use this new tool to force the process to change the login level on the fly. And now you can force the process to start logging on debug without having to restart the thing. So now you can inspect the process, and you can get all this debug output, and then you can make sense of what the hell is going on. This is a real application, and then you can see how you can now get all these IPs and queries that are happening without having to restart the process. This is particularly important for big software, because sometimes restarting applications is a process that can take hours, especially when you have many of them, and then you need to start them in a particular order. In this way, not only you can inspect it, but you can know that the inspection is safe. Like the program won't crash when you do these things, and then you change the login level. Some other ideas that you can have with this is, for instance, inspect some internal state. For instance, here I have a web server, and using this thing, I'm forcing the web server to dump to standard output, but you could do a file or something else, all the internal state, and I can see all the IPs that are being connected at this time to the process, and all the different connections. Of course, you can also call this in a loop, or you can force the program to just call this in a loop or repeatedly, so you can get this information constantly. Some other ideas that you can have, for instance, is that you can inspect the memory, the objects that are alive. This is very difficult to do even for memory profilers, because when a memory profiler attaches to your process, it will only be able to see the memory from that point on. Like, so if your program is leaking memory or something like that, you will not see what has been leaked, because that already happened. But with this, you can actually force the process to go and use the garbage collector, for instance, to print all the different objects and sizes. You could also do the same thing to print what is the biggest objects that you have, in case you have like too much memory. You could also use this thing to print like modules, like what are the modules that I loaded. Or for instance, imagine that you want to see if you have cycles. You see that the process is doing something weird, and you want to force a garbage collection run on demand. Or for instance, you want to see like all the objects for classes. So this is just, again, a building block. We are super excited to see all the different things that people build on top of this. And if you don't want to build anything, you can just enjoy PDB-P, which I think is exquisite. But we are very excited to see what happens from here. So just to close, some closing remarks. So I think like years from now, software engineers will look back at 2024 and they will see how we debug Python applications. And they will see things that are weird practices, like ritualistic restarts of processes, like CRUD tools and superstitions workarounds. Like they will basically ask how they could have worked this way. So I think it's time to put out the bone zone at the leeches. It's time to step out of the debugging dark ages. Like the systems we run these days, they run the modern world, and then we think they deserve modern care. And now, finally, they get it. Thank you very much. All right. Yeah. Questions?
Great talk. I really like it. You went quite deep with modifying other processes. I was wondering, how did you do this on Windows? Did you create a remote thread or some other technique very similar?
With pain. No, so Windows is particularly nasty. The idea is the same. Windows has some other system calls. Actually, the system calls are easy. But the hard part on Windows is managing the paths because they can be UTF-8 6 million or whatever. Yeah. Windows have the same idea and they have their own protection system that the system call leverage. So the process itself is the same. What is different and is really, really, really painful on Windows is PDB minus P. Because this is on top of this machinery, right? Because PDB now needs to deal with things like you press Control-C on the remote PDB and it needs to stop the other one. And that is indeed like quite complicated. So that was implemented in Matt Wodnicki, which is over here. So you can, that guy that is like, he has like a suffering face. You can see his scars. Windows is a tough place. But he's there, and you can ask him to know how he implemented that. But the actual remote exec is the same idea.
Okay, got it.
Thank you.
And also, just to be clear, this is on by default in 3.14?
Yes.
Okay.
As an author of an observability platform that's interested in using this, where do you recommend I start looking for things? The PEP, docs?
So you can start by the PEP, but we also have like a good docs. We have like the process, how we did it, and we have some recommendations if somebody wants to implement this thing, for example, in Rust. We have some recommendations, so you can follow the docs for that.
Great, thanks.
Thanks so much. On this topic of on by default, could you talk a little bit about the design decision behind that? Because I would think you'd want it off by default.
Of course. So these system calls are the same system calls that any debugger will use. So for instance, if you have any C program, these system calls are the one that GDB will use. And you can use GDB by default. So it's not more dangerous than any other debugger. If your platform, for instance, has already protections towards debuggers, like you don't want to execute debuggers, this will automatically follow the same protections. So these things are not new. They are standard debugger calls. And the same way you can use GDB if your system allows it. With any program, you can use this. If your system disallows it in any way, we follow exactly what you're doing. So that is why it's on by default, because really it's just following what you have. In particular, in Linux, if you have most distributions these days have Yama on, which means that you need sudo to execute this. Like you cannot force or read memory without sudo. If you can deactivate this by setting Yama off, but it's the same as GDB. Like if you try to use GDB on Ubuntu, whatever, it will tell you permission deny because you need to use sudo. So, and then depending on Windows, they has its own different system to decide if you can read or not. So it's on by default in the sense that it's compiled by default, but it still will follow all the strict rules that different Linux processes and Windows processes and macOS processes will require. For instance, in macOS always requires sudo. And in Windows, I think it goes through this like crazy system that Windows has for permissions.
Thank you.
Hi, this is awesome, really.
Thank you.
Question, you must be checking the is there anything in my box like millions of times? Did you see any performance impact at all? Thank you.
So actually we mentioned like evil breaker was already there. So you're only gonna check if there's something in the box when you hit the evil breaker, when you actually set it. And of course, if the debugger, remote debugging was already enabled, and if somebody requested the remote debugging, you're gonna see the flag, and then you're gonna execute the script.
So a note on that. So the actual check of the buffer is protected by a boolean. Like basically, is there anything to run? So that is executed on the eval loop with many other booleans. For instance, there we have, I mean, it's maybe more complicated because it's an atomic and whatever. But we have our system to check, should we run the GC, should we check for signals? So it uses the same system. We actually run some performance with perf. Because normally, when you hit that check, the normal thing is that there is nothing to run. The branch predictor predicts this in 3 runs. So at the 3rd run, like the branch predictor always takes the correct branch, so it's negligible. Like it's literally unmeasurable after 3 attempts. I did some examples when you set it every second and then you go and we observe nothing. It's just noise. So like it has 0 impact whatsoever.
How does this interact with execution in extensions?
Right, good question. So the answer is that the same way the signals or the garbage collector will do. So normally, for instance, if you're running a long-running like C extensions, when you grab the GIL and then you don't do anything, then we need to wait until you actually go back into the interpreter to execute anything. But you don't want to do that anyway, because then if you press Ctrl-C, nothing will happen, right? Because signals are checked with the same mechanism. So if you are an author of a C extension and you're running a long-time computation, you want to check for signals. There is a C function called PyRcheckSignals that we are hooking into it. So that function will not only check for signals, but it will also check for this. So if you are doing properly your C extension and you are making Ctrl-C work like everybody expects, then this will work the same way. But technically, you will see a delay, which is potentially arbitrary, between you ask the interpreter to do something and the interpreter actually reaches the save point.
Thank you.
Hi, thanks for the great work and the great talk. I have one question. What if the debugging script results in, like, for example, Python exception? Does like.
All right, that's a very good question. So right now, what we do is that we raise what we call an unraisable error. So that is just printed. It's the same kind of exception that you will get if a thread raises and it reaches top level. Like it doesn't stop the process, it doesn't propagate, it just prints. You have a sys.dot unraisable hook or something. Victor Stiner probably will know better. So you can ask him. Not wearing a banana suit, just for reference. But you can override that and then you can react to it if you want with something else. Like you can log it or whatever. But technically, if the script rises, it doesn't get propagated. So when your actual code resumes, you won't see the exception.
Great, thank you.
Awesome.
Please give a big round of applause to Pablo, Ivona. Great talk.